Um, so today's lesson is complex numbers. And complex numbers, if you get a chance in college, if any of you go into, decide you're interested in math at all in college, if you take a class on complex variables, it's really one of the coolest, one of the most interesting classes I ever took when I was in college was complex variables. It's really really interesting, and it leads to so many different places that you wouldn't imagine. Um, so so far we've been working mainly with real numbers, but even something simple, a simple equation like x squared plus 1 equals 0. We can't solve that with real numbers because we end up with x squared equals minus 1. So our real numbers, even a simple equation like this, our real numbers give us a limitation. And interestingly, complex numbers, the idea of the square root of negative 1 being something that we can work with, came up not because of an equation like this, but to develop, we have the quadratic formula for solving quadratic equations. To develop a formula for solving cubic equations, the person that worked on it needed to come up to develop this idea of complex numbers, even when the cubic equation, all the solutions are real numbers. So in the middle of the process, you have to use complex numbers, even though the solution ends up being real numbers. So the complex numbers originally started being developed to solve a cubic equation. Even though the solutions were real numbers, in the middle of the process, you need complex numbers. So it's kind of a cool idea. So our basic complex number is I, and I we define as the square root of negative 1. And the property of I is that I squared equals negative 1. That's our most important idea. The basic idea of complex numbers is we have this number that we call I, where I is the square root of negative 1, and I squared is negative 1. And it's kind of unfortunate that they gave it the name imaginary, because a lot of people think, oh, it's imaginary, it's fake. But complex numbers come up in lots of applications. Comes up in electric circuit design, comes up in quantum mechanics, comes up in a lot of differential equations and calculus, where you're solving equations. You end up using complex numbers, even though what you're talking about isn't imaginary. So we called I the imaginary unit. So I is an imaginary number, or the imaginary unit. And we write, so anything that's a multiple of I, if we're multiplying I by any number, is called a pure imaginary number. So 3I, 16I, negative 6I, these are called imaginary numbers. If we add a number to this, a real number, if we have 1 plus 3I, negative 2 plus 16I, (3 minus 6I, we call these complex numbers, where we have a real number and a complex number. So these are complex numbers. And standard form, what we call standard form for complex numbers, is anytime we write it as a plus bi is standard form. And a and b are both real numbers. And complex numbers are equal. If we have two complex numbers, only if their real part and their imaginary part are both equal. We call the first part that's just the real number, the real part. The second part that has the I with it, the imaginary part. So complex numbers a plus bi and c plus di are equal only if a equals c and b equals d. So all the parts have to be equal for complex numbers to be equal. And when we add or subtract complex numbers, I'm going through this pretty quickly because you guys have seen this before, and it's pretty straightforward. When we add or subtract complex numbers, we add the real parts and we add the imaginary parts. We don't mix the two parts together. So to add or subtract, we just add the real parts and add the imaginary parts. That's exactly right. So Caitlin says that would be like mixing apples and oranges. We don't mix our real parts with our imaginary parts. So adding or subtracting, I'm just going to do a quick example. If we have 2 plus 3i minus 6 minus 2i, I'm going to rewrite that as 2 plus 3i minus 6 plus 2i. I'm just distributing this negative. And we get negative 4 plus 5i. So I'm just keeping the real parts together and keeping the imaginary parts together. That's how we add or subtract. To multiply complex numbers, we keep the real part and the imaginary part. We multiply everything together, and then we combine the real parts and imaginary parts. So we'll look at an example of that. If we multiply just by a number, if we have 2 times 7 minus 5i, I'm just going to distribute. And that's just going to be 14 minus 10i. And again, I'm just keeping my real part and imaginary part separate. If I have 2 imaginary numbers, 2 complex numbers that I'm multiplying, let's say I have 3 minus I times 5 plus 4i. If I have something like this, I'm going to FOIL and then combine. And remember that I squared equals negative 1. So we can use that to simplify. So let's do the procedure for this. So my first, I get 3 times 5 is 15. My outside, I get 12i. My inside, I get minus 5i. And my last, I get minus 4i squared. So I'm going to combine these. I get 15 plus 7i, and 4i squared is negative 1, so I can write this as minus 4 times negative 1. So finally I get 15 plus 7i plus 4, or 19 plus 7i. So when we're multiplying, we FOIL, and we remember that I squared is negative 1. Any questions so far? Again, all should be pretty straight review.
Can you leave that up for a question?
Yes. Good. All right. Next, we're going to talk about division. And to divide complex numbers, we need the idea of a complex conjugate. To do division, we need a complex conjugate. So a complex conjugate is we change the sign of the imaginary part only. So if I have a complex number 7 plus 3i, the conjugate is 7 minus 3i. If I have negative 3 minus 6i, the conjugate is negative 3 plus 6i. So to divide two complex numbers, what I do is multiply the top and the bottom by the complex conjugate. And we multiply by the complex conjugate of the denominator. So we'll do a couple of examples of division with complex numbers. So let's say we have 2 divided by 1 minus I. So to divide this, I'm going to multiply the top and the bottom by the complex conjugate. So I multiply by 1 plus I. And what happens with the complex conjugate is when I multiply a complex number by its conjugate, I end up with just a real number. So let's multiply this out. So on the top, I get 2 plus 2i. On the bottom, I have to FOIL. So I'm going to write parentheses so I remember I have to FOIL. And we talked about multiplication, so we're going to FOIL, combine, and then simplify. So for my first, I get 1. My outside I get plus I, inside I get minus I, and for my last I get minus I squared. So I get 2 plus 2i divided by, my i's in the middle cancel out, and I squared is minus 1, so this minus I squared turns into positive 1. So on the bottom I just get 2. So I get a 1 here and a 1 here. So I get 2. And 2 is common to each factor. So I get 1 plus I. I can factor a 2 out of each of these and cancel that 2. So multiplying by the complex conjugate gets rid of the complex number in the denominator, and I just end up with a real number in the denominator. And we'll do one more example if I have a complex number in the top and the bottom. So I have 2 minus I over 4 plus 3I. To divide these, I'm going to multiply by the complex conjugate of the denominator. So that's 4 minus 3I and times 4 minus 3I. And I'm going to put parentheses here so I remember I have to FOIL everything. So on the top we get 8 minus 6I. Inside we get minus 4I. And for the last we get plus 3I squared. And on the bottom, when we FOIL, we get 16 minus 12I plus 12I. And for my last, I get minus 9I squared. And I'm going to combine and simplify. So I get 8 minus 10I, and 3I squared is minus 3. And on the bottom, I get 16, and minus 9I squared is plus 9. So finally, I get 5 minus 10I over 15.
How'd you get rid of the I squared?
I squared,
Isn't it 24? Yeah.
did I
16 plus 9.
16 plus 9 is 25. I squared is minus 1. So anytime you have an I squared, you just replace that by negative 1. So this is 3 times negative 1, and this is negative 9 times negative 1. And I can factor out a 5 in the top and the bottom. So this is 5 times 1 minus 2I, and still 25 on the bottom, and I can simplify that to 1 minus 2I over 5. Everybody good with division? All right. The last thing that we and the main reason we're talking about complex numbers is complex numbers allow us to solve the quadratic equation when we have a negative number under the square root. So that's really how we're going to use complex numbers. Is we've been working with solving equations with quadratic equations. Complex numbers will let us find all the solutions to a quadratic equation, even if we get complex solutions. And I just want to do a quick reminder about simplifying radicals, because we'll need to be able to do that. Need to be able to do that a little bit. So when we have complex numbers or imaginary numbers, for example, if we have the square root of negative 8 times the square root of negative 6, whenever you have this negative inside your radical, you want to separate the negative 1 from your number to remind yourself that we're going to have a square root of negative 1 involved in there. So I would rewrite this as the square root of negative 1 times 8 times the square root of negative 1 times 6. And I'm going to separate this out. This is the square root of negative 1. I'm doing more steps than you need to do, but I'm just doing this to remind you how you need to look at this. Square root of negative 1 times the square root of 8 times the square root of negative 1 times the square root of 6. Square root of negative 1 is I. So I get I square root 8 times I square root 6. And that's I squared square root 48, or negative square root 48. So we want to make sure we keep track of these negative ones inside of our radicals, because they definitely affect our answer. So when you see a negative inside your radical, make sure you separate and you take that I out. So what you could do is immediately when you see square root of negative 8, you could immediately rewrite that as I square root 8. And square root 6 is I square root 6. So those i's, you have to keep track of the square root of negative 1 in your radicals. That was the point of this. So I just want to do one quick example of solving, just to show you what this lets us do and kind of point us to the direction that we're going with this. If we had, we want to solve x squared plus 9 equals 0. In the past, when we've gotten to here, so far in this class anyway, when we get to here, we would say no solution, because we can't take the square root of a negative number. This has no solution. But now that we've talked about complex numbers, we're going to say that x equals plus or minus the square root of negative 9. So x equals plus or minus this square root of a negative. I get an I. And the square root of 9 is 3. So I'm going to write this as 3i. So my solutions to this equation are x equals plus or minus 3i. And we could check if we square 3i, we get 3i squared, or sorry, we get 9i squared, or negative 9. And we plug in negative 9 there, we get 0. So this equation, the solution of this equation, is these imaginary numbers. If we do one that's a little more complicated, we want to solve x squared plus 6x plus 15 equals 0. This one doesn't factor. We can't factor this one easily. So we'll use the quadratic formula. X equals negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 15. And all of that is over 2. Just plugging into our quadratic formula. So we get negative 6 plus or minus the square root of 36 minus 60 over 2, or negative 6 plus or minus the square root of negative 24 over 2. And this negative tells me I'm going to have an I, my imaginary number, involved here. So this is negative 6 plus or minus I square root 24 over 2. And I can simplify the square root of 24. Square root of 24, just anybody help me out simplifying that? Two 6, right. Plus or minus 2i square root 6. 24 is 4 times square root of 4 times 6. 2 square root 6. So I get negative 6 plus or minus 2i square root 6. And 2 is common to both factors, so I get negative 3 plus or minus I square root 6. So this is the solution to this equation. My solution is 2 complex numbers. And as we go forward in this chapter, we'll do a little more with these complex solutions and how they work and how they fit into what we've been doing with polynomials. And eventually, before too long, we'll get to what's called the fundamental theorem of algebra, which is a pretty cool thing. Anything that's called fundamental theorem turns out to be pretty interesting, I think. All right, any questions on complex numbers? All right, homework. There you go.